Hello guys, welcome back to another video on my channel. Before watching this video, I urge you to watch the last one because this is a linear algebra lecture series on my channel. Quite unusual to the kind of content I post. And especially because we're going to need the linear dependence lemma or the lemma on linearly dependent lists in this video. So let's get started. But before we actually begin, I have a cool piece of etymology for all of you. The word from last few videos has been span. So, where does the span in our modern language come from? Old English, span, distance between the tips of the thumb and little finger, which traces back to Proto-Indo-European from a root that means to stretch, which is also cognate with the Proto-Germanic spano. And the asterisks here in both these proto languages just indicates that it's part of the reconstruction, that we don't know whether the s should be here because they're both proto languages. So that's the cool bit of etymology. Now let's actually get started. So far we've talked about linearly independent and spanning lists of vectors. We started with talking of linear combinations, then spans and linear independences. And this was all working with a finite size list of vectors. And the highlight of the last video, one of the highlights actually, was that we managed to prove the following result: that the size of a linearly independent list is less than or equal to the size of any other spanning list. So it is natural to try to unify both of these concepts of linearly independent lists and spanning lists. To do this, we have to define the notion of a basis. A basis of V is a list of vectors in V that is linearly independent and spans V. So you have both linear independence and spanning property. An example is the standard one, the list 1, 0, 0, 0, and then shift the 1 to the second position for the second element in the list, and then 1 to the last position. This is a basis of Fn. So you can check the spanning property and linear independence, and it is also called the standard basis of Fn. If you consider the vector space to be the space of polynomials of degree m over field F, then the basis of such a space, and again this would be a finite dimensional because we fix the degree to be m, the basis, a basis rather, would be 1 z so on until z to the mth power. And this is the standard basis of the space of polynomials of degree m over f. And a few non-examples. So the list 1, 2, minus 4, 7, minus 5, 6 is linearly independent in F3, as you can check, but does not span F3. Because to span F3, you need 3 vectors. So it is not a basis of F3. The list 1, 2, 3, 5, 4, 13 spans F2, but it is not linearly independent. So again, it is not a basis of F2. Now a proposition, because we have a definition, we will try to show how other conditions are equivalent to that definition. So a list V1 through Vn of vectors in V is a basis of V if and only if, here's the equivalence condition, every V in the vector space can be written uniquely in the form V equals A1 V1 plus dot 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 AN Vn, where the scalars A1 through AN all belong to the field. To do that, we have an if and only if, so we need to prove both directions. Let's start with one direction. So let's first suppose that V1 through Vn is a basis of capital V. Take any vector, small v in capital V, then because v1 through vn spans v. Why does it span v? Because it's a basis of v. There exist these n scalars, a1 through an, such that v can be written as a linear combination of those vectors in the list. And why can we do that? Because they span v. Spanning a space v means that any vector in that space can be written as a linear combination of the spanning set or the spanning list. So v equals a1 v1 plus dot 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 vn an, where a1 through an are just random scalars corresponding to v. Now we need to show that this is unique. So suppose there were another kind of expansion for v in with respect to this the spanning list v1 through vn, and a different expansion in the sense that we have different scalars b1 through bn, such that we have v equals b1 v1 plus dot 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 bn vn. Then we can subtract both equations, one with the a expansion and the other with the b expansion, to get 0 equals a1 minus b1 times v1 plus dot 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 an minus bn times vn. Now v1 through vn is a basis, so we use the spanning property. Now let's use the linear independence. So v1 through vn is linearly independent, and therefore it follows that recall the property for linearly independent lists, that 0 can only be expressed uniquely where all the coefficients are 0. So that means a1 minus b1 is 0, so on until an minus bn is 0. So we have a1 equals b1, a2 equals b2, so on, an equals bn, just because of one of the properties of linear independence. That's one direction done. Now let's suppose that every vector of the vector space can be written uniquely in the form v equals a1 v1 plus dot dot an vn, where a1 through n are scalars. This implies that the list spans v, because we've just written any vector or every vector of the vector space as a linear combination of the list of n, size n, v1 through vn. Okay, so we're done with spanning. Let's show linear independence. To show linear independence, suppose b1 through bn are scalars, such that they are the scalars for the expansion of 0. So 0 equals b1 v1 plus dot 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 bn vn. Why can we do that? Because v1 through vn spans v, and 0 obviously belongs to v, so 0 can be written as a linear combination of v1 through vn. But we can also write 0 as the expansion with all coefficients 0. So instead of b1, we can have 0 v1 plus dot 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 0 vn. And this is indeed 0 because 0 plus 0 added it with itself n times is 0. Now we use the assumption of uniqueness. So we've supposed uniqueness in this direction. So that means that both these ways of expressing 0 in terms of this list of n vectors v1 through vn must be the same, because we can express any vector uniquely in terms of a linear combination of v1 through vn. So both these ways must be the same. Otherwise, uniqueness does not work. So we violate our assumption. So we can't violate our assumption. Both these ways of writing 0 must be the same. That means b1 equal to b2 equals so on till bn equals 0. All of those coefficients must be 0. And that's all we need to prove that it is linearly independent. Because for linear independence, we needed that 0 be expressed in terms of a list of vectors where all coefficients are identically 0. So that's exactly what we have from uniqueness. So therefore, v1 through vn is a basis. So we've done that direction as well. Proposition, which is important to us. Every spanning list in a vector space can be reduced to a basis of the vector space. How will we do that? Suppose V1 through Vn spans capital V. We would like to remove some of the vectors from V1 to Vn so that the remaining vectors form a basis of V. So let's begin a process where we're setting the list of these n vectors, call that B. So B equals the set of V1 through Vn. In the first step of our process, and we'll start the process from left to right. So we look at V1 first. If V1 is 0, then delete V1 from B, because having a 0 vector does not really contribute anything in terms of a span to the list. So if V1 is not 0, then keep it in B, don't remove it. That's step 1. It's simple. Step K, where K is going from 2, 3, 4, 5 until n. So if Vk, which corresponds to the vector, the kth vector from the left, is in the span of the vectors before it, which is V1 through Vk minus 1, then delete Vk from the list B, because by the lemma from the last video for linearly dependent lists, removing a vector which is linearly dependent on the vectors before it does not change the span. So we can simply remove Vk from the list B. If Vk, however, is not in the span of the vectors before it on the left, then just leave B unchanged. That's the simple step. So after K goes to n, we do this from 1 to n. This process terminates after step n because there's we reach the end of the list, and this produces a list B. And now the list B is actually what we end up with after going through all these steps, because some vectors will get deleted, some vectors will remain. So B is what we get after we terminate the process, what is remaining from the original list. Since we remove linearly dependent vectors, we use the lemma from the last video to tell us that the span is unchanged, because the lemma from before just said if you remove a linearly dependent vector from a list, the span of the original list before deletion and after deletion is the same. So the span of V1 through Vm, which was the original list, equals the span of B, which is the list we get after the process terminates, after we remove those bad linearly dependent vectors. That should still be V, because that was a V, because V1 through Vm spanned capital V. So span B is equal to V as well. And that's actually what we assumed, right? Because we started with a list that spans V, although we should have a Vn here. So at every step, we ensured no vector in B is in the span of the previous ones, just because of the way this process works. And because of that, we end up with the list B, the final list B, which is linearly independent. Because we just gave no chance for linearly dependent vectors to remain in B. We kept removing them. We kept checking if any vector was in the span of the previous ones. If it was, we removed it. If it wasn't, we kept it. So the vectors on the left in the previous steps were linearly independent, and then we checked that the new vector of the step you're in was dependent on them. So this process systematically eliminates linearly dependent vectors from the list, and we're left with the final list, which is linearly independent. Hence, B is a basis because it spans all of the vector space, and it is linearly independent as we've constructed. So it must be a basis. That's it. That's how you prove this. Why this is important is because it gives us a very instrumental corollary. So every finite dimensional vector space has a basis. Now, by definition of being a finite dimensional vector space, and we defined this, I think, 2 videos ago, a finite dimensional vector space has a spanning list, and list has finite elements. So therefore, we have the finite terminologies matching up. The previous result above this corollary tells us that each spanning list can be reduced to a basis. So that's it. We know we always have a spanning list. We must have a spanning list because we have a finite dimensional vector space, and uh, just use the algorithm or the process of changing each spanning list into a basis by eliminating the linearly dependent vectors. And that's it. That's how you prove this. Now we had a result for spanning lists. Let's see if we can prove a similar result for linearly independent ones. So every linearly independent list of vectors in a finite dimensional vector space can be extended to a basis of the vector space. So before, with the spanning list, we had can be reduced to a basis. Here we are falling short of a basis with linearly independent lists, so we have to extend linearly independent lists. Okay, suppose u1 through um is linearly independent in a finite dimensional vector space. Let w1 through wn be a list of vectors in V that spans V. And we can always have a spanning list, because we are working in a finite dimensional vector space. Therefore, the list u1 through um, v w1 through wn. So what I'm doing is I'm adding the linearly independent list with the u elements to the left of the w1 through wn spanning list. So this grand total list spans V, because w1 through wn spans V. We can write each u1 through um as a linear combination of w1 through wn. So this entire thing will span V, because the w1s do. And from the previous result, we can reduce this spanning list that we have to a basis of V. And the final basis that we end up with will consist, however, of all the u1 through ums and some of the w's. Why will it have all the u1s through ums, all the u's? Because in the process we had before, we were deleting vectors that were linearly dependent on the vectors that came before them on the left hand side. So when we are parsing through the u's, we look at u1, we'll keep u1 because it's non-zero. We look at u2, we'll see u2 is not in the span of u1, we'll keep u2, and so on until um, which is also not in the span of u1 through um minus 1, the vectors before it on the left. So we'll end up keeping, by the way we've constructed our algorithm or our process of eliminating linearly dependent vectors, we'll end up keeping all the u's, but the w's will have no such guarantee, because we did not say that the w's were linearly independent. So if anything is going to get deleted, it's the w's, not the u's. And therefore, whatever we end up with is a basis from the previous result, and we're done, because we've extended to a base. We had to end up with a basis. We started a linearly independent list, took any random list of vectors that spans V, and such a list must exist because V is finite dimensional. Added the linearly independent list to the spanning one, said the entire thing spans V. Used the previous result to break this spanning list into a basis, and that's it. That's the end of the proof. Now, as an application of the result above, we will show that every subspace of a finite dimensional vector space can be paired with another subspace to form a direct sum of the whole space. And this result is actually quite important to us, so we'll call it a theorem. Suppose V is finite dimensional and U is a subspace of V. Then there is a subspace W of V such that V equals U direct sum W. You can understand this as a subspace decomposition theorem. So to prove this, we first note that because V is finite dimensional, U must also be finite dimensional. We proved this, I believe, in the last video. Since U is also finite dimensional, there is a basis U1 through UM of U, because you can start with a spanning list, and you must have a spanning list because it is finite dimensional. And you decompose the spanning list into a basis. You can do that, or you can take a linearly independent one and extend to a basis. But either way, there is a basis U1 through UM of U. Being a basis, U1 through UM is a linearly independent list of vectors in V. Because not only is it linearly independent in U, it is also linearly independent in V. This is a very simple fact. You can check this if you don't believe me, but I will not really over explain that. So therefore, this list can be extended to a basis U1 through UM, W1 through Wn of V from the previous result. That if you have a linearly independent list, you can extend that to a basis. So that's what we've done. We've noted that this U1 through UM, which was a basis of U, is actually linearly independent in V and can be extended to a basis of V. So in that extension, based on the proof of the previous one of the previous lemmas we had, or propositions we had, all of the U's will be retained, and we'll have these new W vectors, W1 through Wn, such that this entire thing is a basis of V. So let capital W be the span of these new vectors, which are not U. So W1 through Wn. Now we need to prove that V, capital V, equals the direct sum of U and W. So to show that this is a direct sum, we need two things based on the video on direct sums. That capital V equals U vector space sum with W, and that the intersection of U and W must be the trivial vector, which is 0. So suppose V belongs to capital V, then because U1 through UM, W1 through Wn spans V. Why does it span V? Because it's a basis of V. There exist A1 through AM, B1 through Bn scalars such that V can be expressed as a linear combination using those scalars. So that means V equals A1 U1 plus dot 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 AM UM plus B1 W1 plus dot 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 Bn Wn. So the linear combination of the U's, call that small u. The linear combination with all the W's, call that small w. Since all the U1 through UM belong to the subspace capital U, this linear combination, which is small u, belongs to the subspace capital U. Similarly, W1 through Wn belong to the subspace W, because W was the span of them. Therefore, this linear combination is inside W as well, which is small w belongs to capital W, just because it is a linear subspace. So we have managed to write small v as small u plus small w, where small u belongs to capital U, subspace capital U, and small w belongs to subspace capital W, which is saying that small v belongs to capital subspace capital U summed with subspace capital W. So that's this first criteria checked. Now, suppose that we have V belongs to the intersection of U and W. Then there exist scalars A1 through AM, B1 through Bn, such that V can be written as a linear combination of just U. Because V belongs to the intersection, V belongs to capital U, and V belongs to capital W. So that means if V belongs to capital U, we can write V as a linear combination of the bases of U, which is A1 U1 dot 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 AM UM, and we can also write a V as a linear combination of the vectors W. So B1 W1 plus dot 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 Bn Wn, because the W's span capital W. So we can subtract both sides to get A1 U1 plus dot 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 AM UM minus B1 W1 minus dot 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 minus Bn Wn equals 0. I'm just subtracting one side from the other. Now we will use that U1 UM W1 Wn is linearly independent because it's a basis. This means that all these coefficients have to be 0, because 0 can only be written uniquely if it's a linearly independent list. So that means A1 equals dot 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 AM equals B1 equals dot 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 Bn equals 0. So all of these coefficients are identically 0. So if all these coefficients are identically 0, what does that make V? Well, that makes V that we took that lied in the intersection to be 0. So any vector in the intersection will be 0, meaning that the intersection of U and W must be the trivial subspace. And that's it. That's proved. So we indeed have a decomposition of V in terms of one subspace and direct sum with another one. Now, before I end this video, a small punchline about bases. Suppose V1 through Vn is a basis of V, then it spans V, of course. And using this inequality from the last video, that the size of linearly independent list must be less than or equal to the size of a spanning list. We know what the size of this spanning list is. It's n. And we said it's a spanning list because it's a basis. So we have the size of linearly independent list is less than or equal to n. But we note that V1 through Vn is also a linearly independent list. So V1 through Vn, this basis is such that it is actually saturating this inequality. If you had taken any other linearly independent list that was not a basis, it would have been strictly less than n. Just because this is a basis, we saturate this inequality to make it an equality. So you can say that a basis is a maximal linearly independent list, because any other linearly independent list that is not a basis will fall below this n. It won't be equal to n. It will be strictly smaller than n, and being a basis is the only way of reaching this upper bound. So that therefore a basis is a maximally linearly independent list. Similarly, we have V1 through Vn is a linearly independent list. So we can set the lower bound to n because we know what the size of that linearly independent list is. So n is less than or equal to the size of lists that span V. But we know that V1 through Vn is also a list that spans V. So because it's a basis, it will saturate this inequality again, like it did with the one before, or the one on top, such that if we had any other spanning list that was not a basis, it would be more than n strictly. So that means a basis is the only kind of list that will saturate this and attain this lower bound. So a basis, therefore, is a minimal spanning list. So you can combine these things together and say that a basis is a maximal linearly independent and minimal spanning list. That's the punchline. So the basis is the best of both worlds. When the spanning list becomes its smallest size, and if you can find the largest linearly independent list in a vector space, then when both of them meet, and they will meet because they have to saturate this inequality, that will be called a basis. So Stay tuned for more content. Peace out and keep doing math. See you later.